having an M squared over there? Michael and Micah, M squared.
Oh, I don't know. Well, here's what it was.
They
They are here. They were finishing their last week's
All right, let's go ahead and get started. So we'll finish up this chapter. Are there any questions on this chapter before we kind of continue? All right, so let's go over some more molecular geometry. And you kind of got a taste for it yesterday, but I just wanted to go over some more common examples of these geometries so you can feel pretty comfortable. And so let's start off with, see if you can draw your Lewis dot structure for BF3. So what would that look like? I have one more, otherwise I can make more copies. Oh, yeah, you need one too? Yeah, let me steal this one and I'll make a copy.
I put stuff right here, but I
Okay.
I just didn't know where to put it.
So did we finish drawing BF3? You want to put it on the board for us by any chance? Let me get out a marker. I was going to toss you a marker. You almost had it. I can't say my throwing skills are very good, so. So that looks pretty good. Is that what everybody else got? And so again, just keep track of your total number of electrons. So of course, boron contributed 3, and then fluorine, each one of those was 7. So 24 electrons total. And then what do you notice about boron? What's kind of funny about it in this structure? It's totally correct. What's just funny about it? Any thoughts?
Is it giving away all its electrons?
Yeah, well, that's one way to think about it. And so, right, you can think about, well, it has only 3 valence electrons. They're all involved in bonding. But then how many total electrons does it feel? So 6. And what's our rule again? What's kind of the rule that we always say that they're satisfied by? 8, the octet rule or the duet rule. And so yes, it's okay if it's a little electron deficient, but again, this is going to tell us a little bit about its reactivity. So these compounds, so boron trifluoride is an extremely angry fuming liquid, and that's because it wants to bond with oxygen and get to the octet. And boron is also of relevance in research because it can do a lot of what's called these like frustrated Lewis pairs, because it does this weird like 3 bonds, but then it still wants those 8 electrons, so it might participate in other bonding scenarios. All right, good. So this is kind of your classic trigonal planar, and so again, this is kind of awkward. And aluminum chloride also follows that same pattern of just being trigonal planar, and again, how you drew it was excellent. And so again, we can see there's no lone pairs. And so we can verify with our little VSEPR chart. So it's 3 electron pairs, right? So 3 bonding pairs, which again tells us that that is trigonal planar. Does anybody remember a trigonal planar example we might have covered yesterday that involves some other elements? You don't know what it's called, so you could kind of like describe this. What did you say, BF5? PF. So that would be our trigonal bipyramidal. So I'm looking for something that's still trigonal planar. We did. Yeah. Or what did you say? I think. Wait, CH4 is methane. So, but there's something else with C's and H's and 2's. So you were really close. What did you say? So you were like almost there. So it's like OC, and then whatever this like R group was. So I think we specifically looked at this molecule, but we could look at any others. Yeah, so these are just a carbonyl group, and then carbon bonded to 2 other things, or our simplest molecule. And so all I wanted to show with this is, again, emphasizing carbon is bonded to 3 things. And we had mentioned it last time, but I just wanted to re-emphasize again today that all these are trigonal planar as well. And kind of recall. Do you remember looking at this funny structure, benzene, like at the beginning? And so benzene is another example of where we see the trigonal planar geometry at each carbon. And so let's just kind of redraw this so everybody remembers what the heck that stands for. And so is this little thing, and we said that we can move the double bonds around, it doesn't really matter. And then all these carbons are connected to hydrogens. And so we'd kind of mentioned previously that we knew the structure was planar, but again, we're just kind of re-emphasizing. So we have each carbon, it's bonded to 3 things. So every carbon center here has that trigonal planar geometry as well. And so again, that's how we know this whole molecule of benzene then is planar. All right, so now let's go back So now it's time for CH4 of methane for tetrahedral. So that's our classic example. So I'm not going to draw that. But let's look at another kind of classic tetrahedral example. And so try your hand at this one. So now we're looking at ammonium, except now we're looking at something with a charge. And so with these charges, when you do your electron count, if it's positive, you need to subtract an electron. And later on, we'll practice with some other polyatomics with negative charges, and then you want to add those appropriate electrons. So try it out, and then we'll go over it more explicitly. Does someone want to throw ammonium on the board for us? You could also put on that far board, or we have retail space. No, so go for it. You want to go? Sweet, go for it, Ethan. And then just stick a plus sign on it so that we know the whole thing is charged. Yeah, so that looks good. And so let's just go through the electron bookkeeping again so we're all on the same page. So nitrogen is 5. Each hydrogen contributes 1, so times 4. So then we're at 9. But then, again, we have that plus charge. So I'm going to put my plus charge, so that means that I subtract 1. So then we give 8 electrons, so just like it's drawn there. And so I'll draw it in the 3D format. It's fine if you draw it flat. And so I'm just trying to emphasize this tetrahedral. And then, yeah, don't forget your little plus sign on it so you know the whole thing still has that plus charge. So the other thing that we can do, and so now let's get into some formal charges. So now let's introduce formal charges. Let me put this at the top. And so formal charges, they're just another way to kind of analyze our structure. And we hadn't talked about it before, since we were mainly looking at neutral compounds, and while you can have formal charges in a neutral compound, it doesn't always happen. But now that we have this plus sign, we should assign our formal charge somewhere. And so what's the formula for formal charge? So it's just defined as, so first you get the number of valence electrons from your table, basically. Right, so I'll put from P table. So whatever its standard is, and then you do minus the number of bonds, and then subtract. And I always write individual electrons. Oops, if I could spell, sorry. Minus individual electrons. And so you might see different variations of this formula. So that's why I have it written like so. And so let's go through this together. And so let's go back to our ammonium here. And let's just do hydrogen for completion's sake. So hydrogen, and I'm just going to write my little formal charge calculation out here. So now we can say, well, my formal charge is, so number of valence electrons, so 1, so that's just from the periodic table. And then minus number of bonds, so it just has one bond on it, so minus 1. And then there's no individual electrons, and so that just gives us 0 for the formal charge. And that pretty much makes sense, and so all the hydrogens are the same, so we don't need to write 0. But since we do have a positive charge, that positive charge should be centered on one of the atoms. And so now let's do nitrogen. So nitrogen's formal charge. And so now we have 5, again, number of valence electrons just from our periodic table, minus our number of bonds, so 1, 2, 3, 4. So no individual electrons on there. And so now this is telling us where our formal charge is. So instead of writing it just overall showing that we have a plus sign, it's better to write our charge directly on our nitrogen or whatever other atom is holding that formal charge. And so we'll look at other examples and play with this. So let's try another, what will be tetrahedral geometry. So that's kind of your hint. And so see what you can do with phosphate then. So PO4, 3 minus phosphate. So see if you can draw out its Lewis dot structure. And so try to do the formal charges then. So if you have an overall -3 charge, that means you have to have some sort of -1 charge maybe somewhere 3 times. So just play with it. Start with your number of total electrons. That's always a good starting point. Or just start drawing lines and counting electrons. someone want to put PO4 3- phosphate on the board for us? You going for it? Here's another marker too. I don't know. I just want them to be dark enough to see. So let's look at this structure. So I see it, phosphorus. Oops, sorry. I was trying to read it. So we have 1 to each one. It looks like 8 electrons on each one. And so let's start. So first we're going to analyze our structure here once I finish copying it. And so again, just so we're on the same page, let's make sure that we have the total number of electrons correct. So how many does phosphorus bring?
5.
And then each oxygen? So 6 times 4
24.
plus 5,
29.
and then plus 3 with our -3 charge. So 32 electrons. So this looks nice. And so let's look at it though. Can we draw other structures? What are our formal charges? So let's analyze the structure a little bit. And so let's look at the formal charge of one of these oxygens. So they're all symmetric. And so let's go through the analysis. So how many valence electrons are in oxygen?
6.
So 6, so that's just from our periodic table. Then we said minus the number of bonds, so -1. And then I use the term individual electrons. So some people say like pairs of electrons times 2. And so that's 1, 2, 3, 4, 5, 6 minus 6 individual electrons. So what does that give us for our formal charge? Oh, try again. Yeah, -1. And so that's a -1, right, on all these oxygens then, because they're all symmetric. But our overall charge is 3 minus, so we have to have a plus sign somewhere. What'd you say? Oh, sorry, I thought you said something.
I did, but you're explaining it as
Oh. And so then let's try to find that plus charge. It's probably on phosphorus, but let's verify that. So formal charge, so 5 minus, so 1, 2, 3, 4 bonds. Oh, so there's our 1 plus charge. And so we can draw it like this then. And so again, right, this is totally acceptable. So all our charges cancel out. But did anybody draw a different structure? Or different ideas? And so this is a case where we can actually draw what's called resonance structure. So I'm going to redraw this one for a second so I don't get too squirrely. And so again, part of this class is not just memorizing a bunch of stuff. We want to be able to analyze our structures and really try to understand what is it saying, how else can we change them and interpret them and move them. And that's really what's powerful. And so again, we're starting with this structure, so I'm just redrawing. And so this is also why it's so powerful to do this little formal charge analysis. It's, fairly simple, but then we have a hint here. Well, if we have a negative charge and a positive charge, next to one another, we might want to minimize these charges to get a better structure. And so we can do that by taking any one of these oxygens. And so the way I'm writing it is just to try to help you guys see chemistry notation for the future. So we're just looking at these two electrons, and we want to try to move them as a pair. And then I'm going to move them into a double bond. So now I'm going to redraw that. So now I'm going to draw this new product. And so all that means is we took one of the oxygens, made a double bond with those electrons. So we still have 32 total electrons. And then now our formal charges work out a little bit better. So now we're only left with those 3 negative charges, which matches, right, for our overall phosphate charge. So that's good. We've taken away some of them. And so now we can see phosphorus is probably also hypervalent, at least somewhat in this structure. So, right, we have 10 total electrons on phosphorus there. So still tetrahedral, but now we can also draw these resonance structures. So I should have actually used this double-headed arrow. And so resonance structures, all they are different ways of kind of showing where the electrons can be. So we're not changing any of our bonding motifs. So we still have a bond, right, between phosphorus and all these oxygens. But we're just moving this double bond around to kind of give us a better sense of the nature of this phosphate. And so really what we're learning with this structure here, so we have 5 bonds here, right, 1, 2, 3, 4, 5, divided by 4 atoms. So you kind of have roughly 1.25 bonds, right, per phosphorus oxygen. So that's kind of saying, right, it's probably a little bit stronger than just your normal single bond, but we're not quite at double bonds everywhere. And so you just want to understand, too, that our resonance structure is, again, just an average picture trying to describe this. And so you just want to also know that we could draw this, right, with any oxygen having the double bond, so we can move that around. And all those are appropriate resonance structures. And then I'll draw the other one. And so, right, you can just go round and round. And so again, with these resonance structures, we see that the negative charge is always at least on the oxygen. And so again, to get a full understanding of phosphate, we'd have to imagine if we could take all the resonance structures and kind of average them all together, right? So you kind of have a -3 charge distributed among 4 oxygens. So just kind of different ways to think about it. All right, let's finish up with the rest of our geometry. Does anyone remember our trigonal pyramidal example? Some classic ones? What do we remember? Any guesses? Yeah, NH3 or ammonia. So this is our classic trigonal pyramidal example. So it's just good to have that in our back pocket. So we also mentioned, right, all our phosphorus compounds that kind of look the same. So all those, so they tend to have a lone pair with that trigonal pyramidal. And then what about our last one? So what's our classic bent example? So SO2 would be 1. So this is our classic, I would say, V-shaped bent, but always good to know and have that. And then what's our other bent example? Yeah, so water's our other classic. So water is more of the traditional bent with the tetrahedral parent geometry, and then again having that angle of 104.5, is it? 0.9? Yeah, 104.5 degrees there. So are we feeling okay about geometry? So for the purposes of your class, these are, again, the main ones that I would focus on. So our trigonoplanar, tetrahedral, trigonopyramidal, and bent. So all the extras that are on your Vesper sheet, that's more for your enjoyment and understanding as you continue in your educational journey. But again, for your testing, it'll be mainly focused on kind of those basic ones. So feeling okay about geometry then? All right, so now let's look at polar molecules. And so we kind of talked about polar bonds, but now we want to figure out, well, how do we know what's a polar molecule? And so let's draw these out for a second. So draw out methane versus carbon tetrachloride versus this dichloromethane here. So just kind of draw those out, sketch them, what they look like, and then we'll talk about them. And so I'll just draw them so people can check. They should all be tetrahedral. So we're just drawing them out. I should have drawn that better. And so now looking at these, so now we have to determine, so which ones are polar and which ones are non-polar. And so let's talk about, well, what makes a molecule polar or not polar? And so with determining whether something's polar, first you're trying to look at, is the individual bond polar? So both examining every bond, but then you want to answer, is there overall symmetry in the molecule? And so let's look at what the heck that means. And so starting with this first one with methane, so CH isn't considered two polar, so we could go back. Where's our? Let's see, so if we take just the difference, And so all I'm doing is checking the difference in electronegativities. You don't really need to do this for every case since it's more about symmetry, but I'm just trying to show. So again, not very polar, so this is right on the edge of the nonpolar-polar spectrum, but it's mainly nonpolar for our carbon-hydrogen bond. And then if we go back to this structure, so this is what I would call fully symmetric, right? So it has hydrogens on every single one, so it's exactly the same. I'm feeling like I maybe should get the molecule kit if people need help visualizing this, but basically, right, it's the same thing, and it's fully symmetric in all directions. And so what kind of helps us is, so if we go back to this chart, what you're kind of also looking for is it the first one in whatever group it's in? And so if it's the first one, and it has all the same substituents on all the sides, that's usually a good indication that it's symmetric. So again, we're looking at this tetrahedral structure. And so again, it's going out the same thing in all directions. So it is nonpolar. And so now let's look at carbon tetrachloride. And so this one, again, we look at our individual bonds and we can kind of get a sense. And so now starting to look more polar, so let's at least just do the math to give us a sense. Again, not too necessary for when you do this, but it's a good thing to kind of work through now. And so, right, it's getting more polar now, 0.61. And so something that we can do as chemists is we can kind of draw the direction that our bond is in. And so we use this kind of arrow to show where it's going towards, so the more electronegative atom is pulling those electrons towards it. And then I put a little plus sign arrow to help remind us, okay, this is going to be more positive. And so if you take physics, I think they use opposite convention for these arrows. And so I'm just drawing out the direction that they're in. And so this is, again, just trying to help show you guys, well, if it's being pulled out equally in all four directions, we establish it was polar, or we establish it's fully symmetric from, again, our tetrahedral geometry. And again, we have the same atom on all four sides. So even though the individual bond is polar, overall it's being pulled out evenly in all four directions. So this is still nonpolar as well. And so now the difference between these two and now, so now we're looking at chloroform, or not chloroform, dichloromethane. So dichloromethane, so you notice, right, it's what I call uneven. So we have half of it has these chlorines on it, and so we could draw our arrows, right? So it's going to be kind of going out in this direction on one side of the molecule. But then on our carbon-hydrogen side, right, this isn't very polar, so I'm not going to draw arrows there showing it. And so again, we kind of have this unevenness on this one side. We have different substituents on all four, or on rather, right, two of them have the same, two of them are different. So again, we've lost our symmetry, and so now this one would be considered polar. And so other hints that things are polar. And so what do we think? Let's look at ammonia again. So do we think ammonia is polar or nonpolar, and why? And you might want to draw the Lewis dot structure better than how I drew it. I kind of drew it purposely, leaving out some information. And so what do we get for NH3? So now I'll draw it in kind of its more proper format. So what do we think? Polar, nonpolar? What's our reasoning here? What do we say? Do we think it's fully symmetric? So, right, I see some nods for no. And so, right, if you're unsure, so we can look at our chart again. So remember, it's in our 4 electron pairs. So it has 3 bonding pairs, 1 lone pair. But that means, right, it's not fully symmetric. So the fully symmetric version of this, right, would be tetrahedral. So we could say, well, ammonium, right, that is fully symmetric. So fully symmetric and therefore nonpolar. But then what do we think about this one? If you're noticing, so it's not fully symmetric. We have this lone pair group here. So what do we think? Polar. Excellent. Let's try acetone. So what do we think about this molecule? Polar, nonpolar. Oh, and these are CH3s on it. And what did you say? I think somebody said it. I was giving people more time. So what do we think this is? Polar, nonpolar? Polar. And so, right, again, we're looking at our individual bonds. So we have a carbon-carbon bond. So, okay, this is probably not very polar in this individual bond. But then this carbon-oxygen bond, so we know oxygen's highly electronegative. We could draw our arrow that it's going towards this oxygen. And again, right, we have the asymmetry, so we only have an arrow going on one side. So yes, that's a good indication that it's polar. Okay, we're running out of time. Let's try to look at what else I want to hit. Let's see. Now I don't remember why I had this in here. So I think I stuck this in there previously just so we could practice writing formulas. So do we remember how to look at these organic structures and write the formulas? So let's do, well, at least a lot of people are telling me no, so that's a good thing that we practice and we're looking at it again. So kind of a quick refresher as we look at this. And so I gave away what it is, but don't forget, we have some rules, right? So every carbon needs 4 bonds. So if it doesn't, right, add your hydrogen. So remember with these organic structures, they don't show hydrogen explicitly. So that means, right, this little terminal point here is a carbon attached to 3 hydrogens. And so spend some time with this structure. See if you can kind of fill in the hydrogens. Remember, hydrogens are drawn explicitly on oxygens and nitrogens, so it's only the carbon that they don't show hydrogen. And see if you can come up with a formula. I'm just gonna try to write in where the carbons are, so I'm just trying to write in carbon. So right, there's a carbon there. I'm just trying to show where the carbons are, so the carbons are at every point. Notice this carbon already has that H drawn. And these are methyls as well. This already has 4 bonds, this already has 4 bonds, that's 4. And then this carbon has 1 hydrogen, this carbon has 1 hydrogen, this already has 4. And so 2. So I stopped labeling these carbons, but these are all carbons, right? Carbon, 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 carbon. And so does someone want to give me a guess for how many carbons we got? Here's some numbers. I think there's supposed to be more than that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. Is that what other people got? Serving. See some nods. 21. And then hydrogens. So I'll try to highlight it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28. Uh-oh, I think I'm missing some. I'm looking at the answer because it should be 30. Oh, 28. I don't think I counted 29. And I'm still missing one somewhere. Oh, 30. I didn't draw this one in. So this one only had 3 bonds. 1, 2, 3. So H30. And then how many oxygens do we have? 2. So C21H30 of 2. Question, take pictures. So you might have to do this on the exam. Maybe try to pick something a little less crazy. And so in the interest of time, so I have to go downstairs and clean up the Earth Club thing real quick, so I'm going to stop this stream.